Hello, I'm Brad Calder with the County of Warner, and it's a pleasure to welcome you to the 2021 Nutrient Management Seminar Series for January 18th. Today we have the privilege of welcoming Dr. Jeff Schoenau. Dr. Schoenau will be presenting on precision manure management on the Canadian prairies towards more effective use of a resource. Dr. Schoenau is a professor of soil fertility and professional agrologist who works in the Department of Soil Science at the University of Saskatchewan. He holds the Saskatchewan Ministry of Agriculture Soil Nutrient Management Chair in the College of Agriculture and Bioresources, and is a Fellow of the Agricultural Institute of Canada. He was born in Saskatchewan, completed his undergraduate and graduate degrees in the 1980s in the College of Agriculture at the University of Saskatchewan, and has worked there since. He also farms with his spouse Lynn near Central Butte, Saskatchewan. His research, teaching, and extension activities deal with soil fertility and fertilizers, nutrient cycling, and soil management practices in prairie cropping systems. Thank you for presenting to us today, Dr. Schoenau. We appreciate it.
Thank you very much, Brad. I'm really happy to be here to have a chance to talk to you folks a little bit about precision manure management on the Canadian prairies, work that we've been doing towards more effective use of a very important resource, manure. So what is precision manure management? I guess I like to think of it simply as getting that manure onto the field in the right place, at the right rate, at the right time, with the right balance. So I think what you're hearing there, folks, are the 4 R's as it pertains to manure management. And really what we're trying to do is maximize the benefit to soils and crops from the organic matter and nutrients, the important things that are contained in that manure, while minimizing any negative potential impacts on water and air. So we think about the 4R system for nutrient stewardship: right source, right rate, right time, right place. And of course, that pertains not only to commercial fertilizer, but to manure as well. And the 4Rs that I want to emphasize in my presentation today are right rate and right place. So let's start off first with right place. Getting the right placement certainly is important, and technology has evolved over the years to a considerable extent. For example, in the case of liquid manure, really gone are the days where liquid manures were simply sprayed or broadcast on the surface, and the move has over time been to develop progressively better equipment for injecting that liquid manure into the soil. Indeed, injecting that liquid manure into the soil using low disturbance type applicators that do a very good job and are compatible with application of liquid manure, not only into conventional annually cropped fields, but also very low disturbance systems, including application of that liquid manure into forages. So we've come a long way, folks. Liquid hog manure injection is generally then applied in bands in the soil, and over the years we've had a number of long-term plots, in some cases in place as long as 10 or 15 years, and the agronomic advantages of that direct injection of liquid hog manure have been very well documented. And thanks to work with folks like Prairie Agriculture Machinery Institute, who have been instrumental in developing this kind of equipment for direct low disturbance injection of liquid manure into the soil. And agronomic advantages certainly include the effect of good placement on improving the crop response and nutrient recovery. As shown there, some data from some of our long-term trials in Saskatchewan showing that improved recovery of nitrogen when that manure is injected in bands, even compared to when it's broadcast and incorporated, and certainly much, much better than when it's simply broadcast on the surface and left alone. So the main message then that we're getting then is get that liquid manure into the ground. There are, like anything else, there are some potential issues with injection, so it's not completely a rosy picture in the sense that when we get microbial decomposition of manure nitrogen, that results in the production of nitrous oxide gas. So in steps involved in the transformations of nitrogen that, in manure that it undergoes in the soil, we can see there that there's a couple of steps, namely nitrification, where ammonium gets converted to nitrate, and also denitrification, which occurs under flooded conditions, where nitrate gets converted to this nitrous oxide or N2O gas. Why do we care about nitrous oxide? Well, nitrous oxide is a powerful greenhouse gas. Although a trace gas, it's 300 times more powerful as a greenhouse gas than carbon dioxide. So when we think about adding, in particular, liquid manure to the soil, those manures do contain soluble sources of carbon that fuel the activity of microorganisms, including those microorganisms that carry out the transformations like denitrification that produce the nitrous oxide gas. As well, with liquid manure, we tend to be adding a lot of water with those liquid manures, and that can also create anaerobic microsites in the soil with reduced oxygen content that also favor that nitrous oxide production. However, there are ways to overcome this. For example, enhanced efficiency additives like inhibitors that inhibit that nitrification process, that conversion of ammonium to nitrate, can be added to the manure to help reduce losses, including the production of that nitrous oxide gas. When it comes to solid cattle manure, injecting that manure into the soil directly poses a few more challenges. Some work that was done in the past, a collaboration between Prairie Agriculture Machinery Institute and the University of Saskatchewan that I was involved with, looked at the development of a prototype to actually inject the solid cattle manure in the soil in bands. And this unit we were able to employ on a plot scale to look at the effect of injecting solid cattle manure into the soil in bands compared to application on the surface. And in this work, we looked at agronomic and environmental impacts of that placement strategy. And our 3 years of data revealed a slightly better yield and nutrient recovery from in-soil placement compared to surface applications. But the benefits with the solid manure weren't as great as what we typically would see with liquid manure. And that's because the solid manure that we were using didn't have a really high volatilization loss potential to begin with. And the other thing that we found was that the injection did not significantly reduce phosphorus transport in simulated snowmelt runoff compared to other application methods. And that may be because when we were creating those channels into the soil to inject that solid manure, we may have been creating subsurface preferential flow channels. How we looked at the effect of the placement on runoff potential was we actually would collect intact slabs of soil from the field, from our plots. We'd bring them back into the controlled environments chambers and apply snow and collect the runoff from those slabs of soil, intact slabs, as the snow melted. And as shown here from some of the work that Dr. Thomas King did in his PhD work, as you can see there was maybe a trend for the injection to somewhat reduce the losses in snowmelt runoff compared to surface placement, but it wasn't large, and oftentimes it wasn't statistically significantly lower. And overall, we found in-soil precision placement of manure is easier and probably more benefits realized when you're dealing with liquid manure compared to solid manures. The other thing that comes in terms of placement and precision management of manure is the uniformity of the application. And certainly we would expect, and as I'll show you, we do that uneven manure application, non-uniformity, lack of precision across that application across that land area can also result in some problems with things like crop emergence and growth. And indeed, what happens when application uniformity decreases, we have where we have, without that manure, bare spots, which are obviously potential sites for nutrient deficiency, and other areas that end up with over-application. We can have some smothering, elevated nutrient concentration, difficulty in getting a good seed bed, and crop establishment. So another collaborative project between PAMI and the University of Saskatchewan was conducted to take a look at the effects of non-uniform cattle manure application. So I'd like to talk just a little bit about this project. So what was done is taking the actual applicator unit from that applicator that was developed for solid cattle manure injection, and it has 6 outlet spouts on it, and we were able to use this to create different variabilities of manure application in the field in small plots. And so our solid cattle manure distribution set up with the lowest variability, that is only a 10% coefficient of variation, we had the same amount of manure coming out of each of those outlet tubes. as shown below. In order to create more variability, what we did is we took the manure that was coming out of one of those outlet tubes, and we used a deflector panel to put it on top of another row of manure from coming out of another outlet tube. And so what this created is higher degree of variability, greater non-uniformity, as shown here, where now we have pretty much a bare spot and doubled up the application there and reduced some application over here. Our highest variability system, 110% CV, greatest lack of uniformity in application was where we took the manure out of one outlet tube and put it on top of this row here, as shown there. And then we took manure out of another two outlet tubes here and put those together on top of the one here. And that created a high degree, the highest degree of variability or non-uniformity across that field surface area. And we could see that in the plots as shown there. That's me out there in the field in the high rate solid cattle manure application trial plot with the highest variability or non-uniformity of application. And we can see there where we had more nutrients availability, greater crop growth, where we had no manure applied, a bare spot area, nutrient deficiency, reduced crop growth. So we could see that variability in crop growth of the non-uniformity of manure application. Looking at our plot data from that study, this is data here in 1 year where we had oats growing. Now, oats aren't particularly responsive to nutrients, maybe, compared to other crops. They're pretty good nutrient scavengers. But nonetheless, we did see a response of the grain yield of oats to the manure application. We had treatments where we had all of the different variabilities without nitrogen fertilizer, and again, with nitrogen fertilizer, because we've recognized early on in our work that the availability of nitrogen from solid cattle manure, penning manure, in the first couple of years following application is pretty low. And we get a much better growth than if we supplement with commercial fertilizer nitrogen. But without nitrogen fertilizer, we can see here with the low CV, the least amount of variability, we do get a response. But here, the highest variability treatment, CV 110, actually, compared to the lower variabilities, we actually got no response and actually maybe even a slight negative effect even compared to our non-manured control. So we can see that that high degree of variability is not giving us a very good, is resulting in a reduced response or no response to the manure in terms of increased crop growth. Now, when we add nitrogen fertilizer, as shown over here on the right, that tends to get rid of that effect, telling us that really the main impact of that high degree of variability, that non-uniform manure application, one of its main impacts is probably uneven distribution of nitrogen in that field, and as a result, limited crop to that nutrient due to its uneven application in the manure. In 2012, with barley, we had a little bit better responses in that year. And as you can see there, compared to the control, our highest rate of manure application gave us the highest yield. But again, we see that highest variability treatment, the treatment with the greatest amount of variability, non-uniform application of that manure, didn't perform as well, folks. And again, as with the oats, when we had nitrogen fertilizer added along with the manure, it tended to mask some of those effects. And those effects then that we're seeing from that non-uniform application, again, seem to be related to that non-uniformity of manure application having a particular impact on the nitrogen nutrition of the crop. Now, the other thing we looked at is what impact did that non-uniform application have on distribution of phosphorus in the soil at the end of the growing season. And not unexpectedly, what we see here, folks, is that where we have that greatest variability in application, that 110% CV, non-uniform, where we're tripling up the application in areas, doubling up, we can see how that results in a hot spot or area, that indicated in red, of elevated extractable, available, and soluble phosphorus in that soil at the end of the season. In fact, we saw the soil test phosphorus levels in those bands without manure were as much as 5 to 10 kilograms per hectare lower than in the neighboring bands where we were getting a double and triple manure rate. So really that high CV or high variability in solid cattle manure application, folks, is creating hotspots in soluble P. Again, non-uniform distribution that results in less than optimal crop utilization of that nutrient, reduces the response, and also could create, in the form of hotspots, areas that would be particularly sensitive then, or zones for increased transport of that phosphorus off the field in runoff. So really we want driving towards improving the uniformity of application across that spreader width. And certainly the modern new manure spreaders that are out there, like the vertical beater type units, do a pretty good job of actually getting relatively uniform distribution across that spread area. I want to move on now to rate and getting the right rate. And I guess we think about nutrient rate planning as really being a kind of balancing act. We want to be selecting the rate that's going to match crop demand and nutrient removal over time to avoid nutrient loading in the long term. In the short term, this coming season, we need to be thinking about what's the appropriate rate, using our manure test, determining what's going to become available from that manure, and of course our soil test to allow us to evaluate what's already there in the soil, and applying the rate of manure nutrient, as well as possibly some commercial fertilizer supplements to ensure that we have the proper rate of each nutrient and that the nutrients are in balance. That is the proper ratio of available nutrients in the soil following that manure application. And one of the important ratios, nutrient ratios in manure that we consider is the nitrogen to phosphorus ratio, recognizing that a lot of livestock manures have higher amounts of phosphorus relative to nitrogen than what crops typically need. So when you're applying a phosphorus-rich manure based on a crop N requirement, you're going to end up over time with accumulation and buildup of excess phosphorus in the soil. On the other hand, when you're applying manure based on a P requirement, that means because you're applying your phosphorus, you're going to need some additional nitrogen because there's not enough nitrogen there relative to the phosphorus to meet the crop demand. And I've already talked a little bit about that in the case of cattle manure. When we're applying on the basis of P requirement, we're going to need some additional nitrogen there, not only because the N to P ratio is relatively narrow, but also because that cattle manure nitrogen, because a lot of it is in the organic form and has a high carbon to nitrogen ratio, we get relatively little of what's there made available in the first couple of years of application. Now, liquid swine manure is a little bit different. It contains quite a high content, quite a high proportion of the nutrient that is there in a readily plant available form, especially for nitrogen. But what we've found in a large number of cases with liquid swine manure is sometimes that liquid swine manure is low in available sulfur. And so what we find is oftentimes high available nitrogen to available sulfur ratios in that liquid swine manure that's been stored in the storage unit. And what we have observed in some of our long-term trials, in one particular trial on a sulfur-deficient gray soil near Melfort to Agriculture Agri-Food Canada that Dr. Molly and co-workers have collaborated with me on over the years, is we did see significant yield responses on that sulfur-deficient soil when we supplemented the liquid swine manure with commercial sulfur fertilizer. As shown there in one of our trials, even with oats and barley, we were seeing some very significant yield responses to the addition of that supplemental sulfur fertilizer. And certainly with canola, very, very available S ratio if you're using manure, liquid manure in particular, and because of the potential for that sulfur deficiency to quickly arise with a high sulfur demanding crop like canola. With solid cattle manure, this issue with low sulfur content really doesn't seem to arise with solid cattle manure. At least we haven't seen it in any of our trials over the years. But with the liquid swine manure, we do see this low sulfur content relative to nitrogen that has indicated and certainly shown in trials that we can see some benefit from some supplemental commercial sulfur fertilizer, especially with high sulfur demanding crops. So really addressing the challenges through precision manure application, you want to be selecting the appropriate rate or rates, balancing those nutrients if necessary, considering the addition of supplemental fertilizer to ensure commercial fertilizer to ensure that you have the appropriate balance of available nutrients, considering efficiency enhancements like inhibitors that can help preserve that nitrogen, especially under high loss conditions, and using effective application equipment. The last thing that I'd like to talk about is some of our ongoing work on variable rate cattle manure application. And this is some research work that we're doing at the U of S that is underway. That's an interdisciplinary type of project that involves folks from University of Saskatchewan Soils Department, Animal Science, Engineering, as well as our Global Institute of Water Security and the National Water Research Institute. And so what we've been doing, we started this in 2019. It's an ongoing project. We're looking at the effects of feedlot cattle manure on crops, soils, water quality, greenhouse gases in 9 watersheds in land that surrounds our new Livestock Forage Center of Excellence Research feedlot. So what we've got is we've actually got 3 management zones that we've identified. A commercial fertilizer only zone, a rate in which manure, a zone I should say, in which manure is applied at a constant rate and there's no setback used from watershed basins. And finally, a zone we call the precision or variable rate manure application zone, where we are applying the manure at a variable rate across the landscape, and we are using setbacks, staying out of the watershed basin centers in our variable rate manure zone. And within each of those zones, as you can see, we've got 3 watersheds that we have identified, 3 basin areas where we are monitoring. So this started in 2018 with assessment of the background conditions, and then we make our manure applications every 2nd year. So a manure application was made in 2019. We got another one coming up in 2021. We're growing silage barley there every year, and so we are estimating our removal of nitrogen and phosphorus by an estimated typical silage barley crop yield that we anticipate on that land. And based on our estimated removals of nitrogen and phosphorus, then we are making our decisions on manure application rate and commercial fertilizer application rate. The manure application that we are making is based on pea removal over 2 years, and that equates to about 45 tons of manure per hectare as the rate that we're applying to replace our anticipated pea removed in the silage barley. And we're using setbacks from the watershed basins in our variable rate zones. All of our zones are receiving nitrogen fertilizer every year, at least in the first couple of years, to at low availability of nitrogen in the fresh manure that we have seen in our previous work. And only the commercial fertilizer zone, that is our C zone there, that's the only zone that actually receives any phosphorus. In the manured zones, the phosphorus that the silage barley needs is coming from the manure alone. There's no commercial fertilizer phosphorus added in our manure constant rate or variable rate treatments. In terms of developing the prescription for the variable rate solid cattle manure application, we're using nutrient echelon NDVI imagery, and our prescription is quite simple. Those less productive, higher slope regions in the landscape receive greater amounts of manure, whereas the foot slopes, the depressions, receive lower rates. And there's no manure applied in the basin centers according to setback where water may accumulate. And so this is based on NDVI imagery, long-term 16-year images of productivity where we see those those red areas identified as upper slope areas with low productivity that can benefit particularly from the organic matter and manure in the nutrients, whereas those higher productivity areas, lower slopes, depressions, already have higher organic matter, higher nutrient availability. We can cut back or reduce the rate of manure in those areas, eliminate it in our basin centers or our sloughs where there's likely to be little or no benefit from the nutrients and manure and organic matter, and where we want to try to keep that manure out of that water to begin with. And around each of those basin areas then, we have transects running through those basins, 6 or 7 typically, where we are measuring crop yield at each of the transect points. We're measuring nutrient uptake. We measure the residual available nutrient in the soils every fall. We measure greenhouse gases that are produced over the season. And in those basin centers, in the spring of the year, we collect water and analyze it for nutrients in the water. Just to share with you some of our data from our first year of manure application, 2019, what did we see in terms of crop growth in those landscapes? This is in our constant rate manure silage barley yield assessments. And we can see there in our constant rate, we do have that typical trend where the crop yield is higher in the depressions and decreases in yield as we move upslope into those upper slope areas. Where we have our variable rate, what we see is actually less variation in yield across that landscape according to slope positions. Our yields in our depressions are not that much different than our upper slope positions because we put some more manure on those upper slopes and help to increase the yield and the productivity. So what we seem to be seeing is a smoothing out or evening out of yield across the landscape as a result of that variable rate application. Looking at soil nutrients in the fall, in the different zones, what we see in our commercial fertilizer and constant rate treatment, particularly in the foot slopes and the depressional regions where we applied commercial fertilizer and manure right through the depressions and the basin centers, the low spots in the landscape, we see elevated levels of available phosphorus and also available nitrogen in those depressional regions, depressions, foot slopes, and basin centers in the landscape, whereas we don't see that in the variable rate application system. So we are keeping available nutrient levels in the areas where water is likely to accumulate lower in the variable rate application, and that probably explains why we're also seeing lower concentrations of nutrient in the runoff water in that precision application variable rate treatment landscape. So far we've seen the variable rate manure application smoothing out the yield and uptake. The reduction or elimination of manure application in those depressions and basin centers, at least so far, we're not seeing any yield penalty associated with that. We are seeing some accumulations of nitrate in the upper slope positions because of that higher rate of manure application there. And maybe in dry years like we've had, increasing rate on that upper slopes may not always be beneficial. No accumulation of available P or nitrate in those lower slope positions that folks really, I think, points to a benefit from reducing the rates in those landscape positions. And also we're seeing lower phosphorus concentrations in the runoff water and lower nitrous oxide emissions as well in the variable manure rate landscape treatments so far. So we're continuing this work on. In 2021, we're going to make another manure application across those landscapes and continue on with our commercial fertilizer landscape comparison and continue to monitor what's going on. I think the message we're seeing so far, folks, is keep that manure out of the sloughs. So really, I think what we're seeing, and I think what we've shown is that precision approaches to manure management and placement and rate certainly offer not only agronomic, but also environmental benefits as well. And I'd like to thank the workshop planners for the opportunity to share thoughts in this webinar today, to thank the many funding agencies over the years, especially the Agriculture Development Fund, to the many collaborators, including Prairie Agriculture Machinery Institute, and especially to Dr. Molly at Agriculture Agri-Food Canada, Melfort, when he was a research scientist there, worked with us very closely over the years on these manure projects. And all of the folks at the University of Saskatchewan, students and staff who have worked in the area of manure management with me. So with that, I will conclude. Thank you. And I'm happy to entertain questions.